As sand leaks out of a hole in a container, you thought I was about to rap. Yeah, right, I can't rap. As sand leaks out of a hole in a container, forms a conical pile whose height is always the same as its radius. The height of the pile is increasing at a rate. Whoa, calm down there, white boy. Let's go ahead and start drawing some stuff if necessary. We know we have a cone. Normally the stuff I don't see, I make the dotted line. And we'll just go ahead and apply a different color here. We've got a height. We're going to have a radius. And I did not draw this to scale because of this statement right here. The height is always the same as its radius, so obviously my picture is misleading. But if this is the height, this is the radius. This picture is kind of unnecessary. It just helps us visualize it. We have sand leaking out here. Blue sand. I don't know where blue sand comes from, but yeah. Anyway, not a geologist, okay? Dang it, Jim, I'm a mathematician, not a geologist. Okay, based on the first sentence, the height is always the same as the radius, so the height is the same as the radius. That's going to come in very handy. Let me give you a hint for some of the other problems. Going to get off topic for just a little bit and ignore this problem. Sometimes it'll say things like, twice the height is equal to the radius. Or it might say, it might give you a ratio. It might say that the radius is 2 when the height is 5. Let's say that again. The radius is 2 when the height is 5. It'll do one of these things, and it will allow you to set up a ratio in which you can solve for the variable that you need to plug in to the other one. So for example, if we're going to solve for h, we'd have that. Or if we were going to solve for h in this case, we would have cross multiplying 5r. This does not happen in this problem, but I just wanted to point it out. So 5r over 2, you know, things like that. So about to erase that. Take one last look at it. This is about to get gone. There we go. All right, so far we've dealt with the first sentence. We drew a terrible picture and know that the height and the radius are the same, not drawn to scale. If the height of the pile is increasing at a rate of, height, rate, that's dH dt. 6 inches per minute. 6, we'll put the units on it just because it looks like fun. Find the rate at which the sand is leaking out when the height is 17 inches. So we know the height is 17 inches. That's a terrible 17. There we go, that's better. And then we're kind of left thinking, what were they asking? Find the rate at which the sand is leaking out. When you're finding the rate at which the sand is leaking out, it's a volume issue. Even though it never said cubic inches, let me give you a couple hints. First of all, if I want to know the rate at which I'm filling up a bucket with water, it's going to be a volume issue. Cubic centimeters, cubic inches, or something more practical like gallons or liters or something like that. Also, another dead giveaway is the fact that I'm going to be dealing with the height and the radius, and generally, when I have the height and the radius, both with a figure like a cone, it's a volume issue. So let's come over here and write the volume formula. Volume equals 1/3 pi r squared h. Okay, let's stop and think about it. What do I know the most about? I know a whole lot about my height, and I was told nothing about the radius other than this right here. So the radius needs to go, and the height goes in its place. I'll say that in a different way. We are going to solve for r, well that was pretty easy, and then plug h in its place. And so volume equals 1/3 pi r squared h. That step is somewhat unnecessary because you can see where this is about to go. 1/3 pi h cubed. All right, we are ready to take a derivative now with respect to time. We'll just put this up here really quick. dv dt equals 1/3 times 3, that's 1, times pi, that's pi, h squared, dH dt. And now we can just plug some stuff in. This is going to be very easy. Let me do this. Pi times h squared, 17 squared, times 6. Okay, pi times 17 squared times 6. We're going to round the 2 decimal places just because it makes sense. 5447.52. And that is a rate of change of the volume. Let's carry this dV dt down. dt. And since it's volume, it is cubic inches. But it's a rate of change, so it's cubic inches per minute. Okay, this one was relatively easy compared to some other ones, and I've given you a couple hints already about what to do in a situation where you have a ratio in which you have to solve for one. But let me say something else that's somewhat related. I'm going to make something up really quick. It has nothing to do with this problem, but it will help you in the future. Let's suppose you've been given something like this, similar to what we had over here. I'm just going to make something up. dv dt equals, not exactly this, but something similar. Again, just making it up. Don't panic. Don't be like, that's not on my paper. Well, you'll be all right. 1/2 pi h cubed dh dt. And let's suppose in the problem you had to solve for dh dt. There's a hard way to do it and there's an easy way to do it. Let's do it the easy way. I'm going to make up some stuff and pretend like I've got the problem down to this point. Let's suppose the dv dt was 3.2, and we have 1/2 pi, and let's pretend like the h was 7. And we want to know dh dt. Some of you would do this in several steps in the calculator, drive yourself crazy, and you wind up with a lot of rounding error if you're not careful. So in a situation like this, my recommendation, the best thing to do is to type this, 3.2. Flip that over, we need to multiply by the reciprocal. 3.2 times 2. We would need to divide by pi. We would need to divide by 7 cubed, and whatever we get is our answer. Now I'm not going to worry about the actual answer. I was just showing you what to do in the calculator to make your life a little bit easier when you're solving for something on this side and all that mess is in your way.